In this video, we're going to be breaking tools, burning things, and exploring all kinds of different end mills and insert mills on the DMC2. In this video, I want to show you how the DMC2 performs cutting metal, focusing on 6061 T6 aluminum and 1018 cold-rolled steel, and then some tool steels at the end as a bonus. I'm using basic carbide end mills that I sell on the Sheriff DMC store, but regardless of where you get end mills from, they'll all perform pretty much the same before you get into more fancy tool coatings. I started off doing tests for ideal feeds and speeds with my tools that I sell, using the manufacturer's provided parameters, and then stepping them up gradually and seeing just how much the DMC2 and the tools themselves can tolerate. In this video, I'm going to show you the more drastic of all of these tests because the intent is to see what the DMC2 can really handle when you push it, and also how hard I can push the tools themselves. Keep in mind that a lot of these cutting parameters that you'll see are not ideal and will result in breaking or prematurely wearing down the end mills. For more conservative and correct feeds and speeds, you can refer to the link in the description where I've organized my test results, as well as posted manufacturer recommended feeds and speeds. There are two main things that I'm looking for when I test tools. The first is that I'm not exceeding the surface speed of the tool, which tends to lead to a screeching sound, and the second is that when I get to a comfortable speed, I gradually increase the cutting loads until the machine itself struggles to keep up. It's a complex balance of speed, feed, RPM, torque, heat, and so on. I'll have a video in the DMC2 training series going over all of this in more detail. For now, this video is just to show off what the DMC2 can accomplish with simple carbide tools. I'm going to do two tests with every tool. First, shoulder milling, which is where you use the side of the end mill to do the majority of the work, and secondly, slotting, which is where you use the full diameter of the tool and just a small amount of the bottom to remove material. I'm going to show you the final results of each test, which is the maximum I was able to push the tools before they break or the machine bogs down. So the DMC2 has an ER20 collet built in. This means it can hold up to half-inch diameter tools, however I'm using metric, so I'll be testing 1 through 12mm tools, and some 10mm carbide insert tools. I'm going to be using pieces of aluminum and steel for profile milling with the small tools. In Fusion 360, I've modeled a 0.5-inch square extrusion for the 1 and 2mm tools, and a 1-inch square extrusion for the 3, 4, and 6mm tools. For the larger tools, I'm just doing a single pass in a large block of material. So starting off with the smallest tools first, the 1mm 3-flute carbide end mill in aluminum. I'm shoulder milling with all tools at full depth of cut, and increasing the step over slowly after each successful test. With the 1mm end mill, there isn't much to see or hear since the tool itself is so small and fragile. So I've included a clip of almost the maximum I was able to push the tool, as well as a clip of when the tool broke at the maximum. You can barely hear the difference, and the machine itself has no idea it's broken, so I manually have to press the E-stop. Now moving on to 2mm tools is when things really start to pick up. That was a heavy cut for the tool, and just for fun, here's an even heavier one where the tool breaks. Now onto the 3mm tools. This is again a very heavy cut for the tool. And here's a 3mm tool pushed even harder until it breaks. What I wanted to point out is that you can hear the spindle start to bog down before it snaps. I'll let the rest of the videos play out and just mention anything interesting as we go. So now the shoulder milling with the larger tools at full depth of cut. I'm starting with the larger depth tools first so I can reuse the same stock material for each test. So right there, the 10mm end mill actually just barely stalled at the end of that cut. I wanted to include it to show that even with that, the machine was still able to produce a really nice surface finish. All of these cuts are actually leaving very smooth surface finishes, although I'm not going for clean finishes right now. I'm just trying to push the machines as much as possible for the sake of proving its capabilities. So that was around the heaviest cut I did with an 8mm tool in aluminum. And here's the same cut from a different angle, just so you can see the chips flying off. I have the cover off of the machine right now so that I can get a good camera angle, and there's plastic wrap on the right side to catch the chips from falling on the ground. And you can see how quickly it fills up with these long curly chips. Alright, so now here's the 10mm insert mill that I sell with the DMC2. This tool is amazing at facing, but not so efficient at shoulder milling since it only has one cutting flute. But here's the test anyways. I have inserts here for both steel and aluminum, and what's awesome about them is that they can run at even higher surface speeds than regular carbide, and leave better facing finishes than an end mill, which you'll see later on in the slotting tests. The surface it leaves is pretty much the same, semi-mirror as the end mills, but because of the flat geometry and single flute, the cut is louder as it smacks into the material, and it also has to be run at 1/3 the feed rate of an end mill to get the same chip per tooth. So now for the slotting tests. I started off with a chunk of aluminum, and I did a bunch of test slotting with each of the smaller end mills. Again, I'll show you basically the final results of how hard I could push the tools and the machine. I am running the tools a little higher than the recommended surface speed, but they seem to be holding up fine. So with the 1mm tools, not much to see or hear again, and the tools break without a sound, so you really need to be careful not to feed them too hard. The 4mm tools work really well on the DMC2 for slotting. The diameter is in that sweet spot where you can run at max power and remove a good amount of material, which makes them really ideal for slotting parts out. 4mm tools are generally my go-to for cutting parts out of flat material, and of course if you push them too hard they do break too. Next is a 6mm test, and I included this test anyways because you can hear the tool struggling, not on the cut, but actually on the ramp down. Eventually I e-stop this when I hear the spindle bogging down. Here's that entire chunk of material. You can see all of the cuts leading up to breakage all look the same and went very well. No chatter or bouncing is visible in the walls of the cut. The 4mm tool looks like it actually gummed up with aluminum and broke because of that, which is a sign that things were getting too hot despite having flood coolant. You can also see where I e-stopped on the 6mm cut and how aggressive the ramp down was at that speed. For the rest of the slotting tests, I'm just going to use another chunk of stock material and face down the top incrementally deeper and deeper each time. For the next tests in 8, 10, and 12mm, you can kind of tell in the reflection that the surface finish is very good. Again, I'm not going for a mirror finish, but we're still getting a decent one despite being at around the maximum material removal rate. And now the 10mm insert tool. The finish it leaves is better here, and that's mainly because the tool has a flat wiper section on the bottom, which leaves a flatter finish than the end mills. So that's all for the aluminum tests. Now on to the steel. I'm using 1018 cold rolled for all of these tests, and I'll repeat everything I did for aluminum now in steel. Starting off from the 1mm again, this time all of the tools are 4-flute and coated carbide. Nothing exciting to see here, the machine hardly feels any load with the tools this small. Moving on to 2mm now, this is an early slower test I did, but I'm including it because the end gets a little crazy. Despite sounding relatively quiet, a lot of heat is still generated in the machining process, which is why a good flood coolant system was mandatory on the DMC2. So what happened there is as the end mill got closer to finishing, the middle section of the material got thinner and thinner and had to dissipate heat. As that heat builds up in a tiny volume of metal and has nowhere to go, it just keeps increasing until things start to get red hot. The tool is fine, but this obviously isn't an ideal cutting situation. I had the flood coolant off for most of these tests and was using a spray bottle for the sake of getting a better video, so normally this wouldn't happen. Now let's see a real faster test with this on the 2mm tool. So that's shoulder milling with the 1mm through 6mm tools, and now I'm going to switch to a larger piece of stock for the larger tools, same thing as the aluminum. So the first test with the 12mm tool completely stalled. You can hear it bog down, and then I hit the E-stop. Now a proper heavy run, throwing a lot of good sized chips. So that's the 12, 10, and 8mm tools. I wanted to point out again, all of these heavy cuts are still leaving very smooth and reflective surfaces, despite being as hard as possible on the machine. And now for the insert mill. I did also switch to the steel cutting insert on the same shank. Again, not the best tool for shoulder milling, but the surface finishes are okay, probably not as good as using a regular end mill. So now on to slotting and steel. Here's the 2mm end mill, nothing too exciting going on with small tools. I did a bunch of tests as usual in a flat bar of steel, but the video didn't come out great, so from 3mm and up, I redid the test spacing a smaller block of the same 1018 material. I had this step over here wrong, but that's fine for slotting tests. You can really see the slotting here, which is great. All of these tools left a great smooth surface finish on the top. Now testing the insert mill. So the surface finish this tool left was amazing, far better than any other tool. Again, this cut is not even optimized for a finish pass, but the results are still great. The insert mill is definitely a tool you want to have around for facing and finishing the tops of parts. Okay, so that's all of the tests done with both 1018 steel and 6061 aluminum. Now as a bonus, I went to metal supermarkets and grabbed one of every piece of tool steel or material I could find on their cutoff shelf to do some random testing. So here's the lineup of what I have. I have D2, A2, 8620, 01, and then regular 4140, and a piece of copper I found on the shelf. What I'm going to do with each of these materials is pocket out a little square with a 4mm end mill, which has a smaller square inside at a 45-degree angle. I'm doing this so that I can measure the inner square after for accuracy, since each face is made by a combination of both axes moving at the same time. Any mistake from one axis would ruin the flatness of the little square inside. This end mill, by the way, is an HRC 65 hardness, so it's meant for doing even harder steels and should have no issues with any of these non-hardened tool steels. So they all turned out great. Interestingly, by the time I finished all of these cuts, the first few materials already started to flash rust on me. This isn't because of the flood coolant though, which has rust preventatives in it. This is because I washed all the chips off in a bucket of water and just left the parts to dry on the table. And yes, I know copper is not a tool steel, and this is the wrong end mill for a non-ferrous material, but just for the sake of getting as many tests in as possible, I threw it in the mix anyways. A soft material like copper is incredibly easy for the DMC2 to machine anyways. So now measuring the inner square. These were machined with a very fine finish pass and should come out to 6mm across each flat. My calipers are nothing high-end, and this is definitely not the best way to measure, but it'll still give us a good idea of how accurate the parts came out. Measuring them all, they each come in at about 6mm plus minus maybe 0.01mm, and that's excellent. Some of this deviation is maybe even due to me not holding the calipers correctly or consistently. So that's all for this test video. I hope it gives you a clearer picture of what this machine is capable of. I don't want people to categorize the DMC2 with other desktop CNCs or routers out there, because this is a whole different league of rigidity and was designed specifically to handle milling steels. It's obviously not a big VMC, but it strikes a balance of cost to performance that I don't think you can find elsewhere. I hope you enjoyed and learned something new from this video, so subscribe for more and maybe share this video with anyone else you think could use the DMC2 for their work. Thanks for watching.